So imagine you ask an AI agent to put a candle in a toilet.
Which, I mean, weird request, but sure.
Right, but it's a standard embodied AI benchmark. So the agent navigates to the bathroom, realizes it doesn't have a candle, and instead of searching the house, it just panics. It grabs a roll of toilet paper, tries to shove it onto the toilet paper hanger, completely forgets the candle, and just repeats those actions until it hits a hard step limit and fails.
Yeah, it just gets stuck in a hallucination loop.
Exactly. And we are looking at a paper today that fixes this exact failure mode. Welcome to AI Paper Slop. We are jumping straight into a paper called SEED, which stands for Self-Evolving On-Policy Distillation for Agentic Reinforcement Learning.
This is by researchers at Tsinghua University, Zhejiang University, and several others.
Yep. And the core insight for you right up front. Outcome-based reinforcement learning for agents is severely bottlenecked by sparse episode-level rewards. This creates a massive supervision gap.
Right, the model doesn't know which specific tokens caused a success or a failure.
SEED solves this by having the model analyze its own completed trajectories to extract natural language hindsight skills.
And then it distills those skills back into its own token-level decision-making process.
So you get dense token-level supervision that dynamically evolves alongside the policy itself. For you ML engineers tuning in, the practical takeaway is a huge improvement in sample efficiency and task performance, with zero extra prompts or compute overhead at inference time.
Which is exactly what you want when deploying these models to production.
To really appreciate the elegance of what SEED is doing under the hood, we should probably map out that baseline pain point a bit more. We're obviously moving away from single-turn text generators toward multi-turn agents, right?
Absolutely.
Like, we want them to use tools, navigate web pages, and interpret complex environmental feedback over long horizons.
Right, which completely changes how we have to optimize them. Like, typically you train long horizon agents using outcome-based RL, stuff like GRPO, group relative policy optimization.
Where you basically sample multiple trajectories, compare the outcomes, and update the policy based on which one did better.
Exactly. But in environments like Web Shop for web navigation or, ALF World for those embodied tasks, the rewards are incredibly sparse. Like, they are almost exclusively assigned at the very end of the trajectory.
So the agent makes, 30 sequential decisions.
Yeah, and only at the end does the environment give a scalar reward, which is essentially just a binary success or failure flag.
It's like trying to learn how to cook a complex 5-course meal, but the only feedback you get is a food critic at the very end saying, well, this tastes bad.
That is a perfect analogy.
Like, you have absolutely no idea if you burned the soup, oversalted the steak, or if, the dessert was actually perfect, but ruined by the main course.
You really need step-by-step credit assignment to actually improve your technique. Because if an agent fails a 30-step task, that whole trajectory is penalized, even if 29 of those steps were totally optimal.
Just because of one bad move.
Right, the failure was maybe caused by a single hallucinated tool use at step 12. But conversely, if it succeeds, the scalar reward doesn't isolate which specific subgoal or clever observation was the magic ingredient. The model is just left guessing.
And that's the supervision gap. You are measuring an episode-level outcome, but you need to optimize token-level policy weights.
Which is really hard to do efficiently with just standard RL.
So if fine-grained decision-level credit assignment is the bottleneck, how do we get it? Because we obviously don't want to pay for massive data sets of human annotations at every single step.
No, that's way too expensive and it doesn't scale. The answer this paper proposes relies on exploiting the agent's own hindsight.
Okay, so how does that work in practice?
Well, we can leverage a fundamental asymmetry of information. Acting in the moment is highly constrained by uncertainty. But looking back after the fact, the full trajectory reveals obvious subgoals.
Sure, and clear failure points that weren't obvious initially.
Exactly. The path through the maze is obvious once you've hit the dead end and can trace your steps backward.
But using an LLM's hindsight isn't a completely new idea, right? Like, people have tried verbal reflection or episodic memory banks.
Yeah, or having the model write experience summaries. They definitely have. But those previous methods almost always introduce severe friction at deployment.
What kind of friction?
Well, they typically store the hindsight as static experience, like in a vector database. Or they require the developer to retrieve long, expensive skill prompts and stuff them into the model's context window during inference.
Which just balloons your compute costs.
Yeah, it eats up your token limits, increases latency, and makes the whole system fragile.
But wait, not to mention, if the model is learning from a static database of past experiences or from an external teacher model, doesn't that guidance get stale incredibly fast?
It really does. It becomes obsolete.
Because as a model trains and gets smarter, its frontier of incompetence shifts.
Yeah.
Correcting a basic navigation error is useless to an advanced agent that's now struggling with complex, multi-step logical edge cases.
And that distribution mismatch is a massive problem in standard distillation. It's actually the primary reason the SEED framework relies on policy distillation, or OPD.
OPD. So that's where the self-evolving part of the title comes in.
Right. It's self-evolving because the supervision is tightly coupled to the exact states, actions, and failure modes that the current version of the model is experiencing.
Oh, I see.
The hindsight skills adapt instantly to address the specific edge cases the policy is currently failing on. The supervision updates in lockstep with the agent's capabilities.
That's really clever. Let's break down the mechanics of how the architecture actually pulls off this on-policy loop, because they split this into a two-stage process.
Yeah, two distinct stages.
But how do we even get a base model to the point where it can generate useful hindsight about its own actions in the first place?
Well, stage one is hindsight skill supervised fine-tuning. Before the model can act as its own teacher, it has to learn what good teaching looks like.
So they have to prime it somehow.
Yeah, exactly. The researchers took the base model and fine-tuned it to act as an analyzer. They used a powerful external model, GLM 5.2, to extract high-quality hindsight skills.
And they did this from 1,440 completed trajectories across 180 different tasks.
Yes, which is a surprisingly small but highly effective seed dataset.
So they are showing the base model examples of full trajectories, both successes and failures, alongside these crisp natural language rules that capture the core workflow.
Right, or the failure correction. They're basically seeding the model with the structural capability to look at a dense, noisy interaction history and distill it down to a generalized, reusable strategy.
Okay, so this stage 1 SFT ensures the policy understands the format and the level of abstraction required to generate useful hindsight.
Yes, which is critical for the next step.
Which brings us to the core loop of the framework, stage 2, self-evolving on-policy distillation.
This is the really interesting part.
Yeah, because during training, the model is playing two distinct roles simultaneously. It is the actor out in the environment collecting trajectories, and it is the analyzer looking at those trajectories to generate skills.
Exactly, it's doing both.
But walk us through the math here. How does a natural language rule actually shift the token probabilities in the base policy?
This is where the methodology gets incredibly elegant. So, for any given action in a sampled trajectory, SEED calculates the token probabilities twice.
Twice, during the training loop.
Yeah. First, it computes the log probabilities of the action tokens under what they call the ordinary context. That's just your standard system prompt and observation history.
Okay, standard baseline stuff.
Then, it computes the probabilities a second time under a skill-augmented context, where the natural language hindsight skill the analyzer just generated is dynamically inserted into the prompt.
Oh, wow. So the model is comparing what it actually did in the moment against what it would have done if it had the benefit of hindsight advice sitting right there in its context window.
Conceptually, yes. And mathematically, the difference between those two probability distributions forms the basis of a dense token-level distillation signal.
Like a KL divergence penalty.
Very similar to that, yeah. If a specific token is strongly supported by the skill-augmented context, it receives a positive push in the gradients. If a token goes against the hindsight skill, its probability is suppressed.
So SEED effectively converts trajectory-level natural language hindsight into fine-grained, token-specific gradients.
Exactly. It maps high-level reasoning directly onto the low-level weights.
But hold on. If the current policy is generating its own advice to teach itself, isn't that just the blind leading the blind?
That is a very common concern with self-improvement loops.
Like, if the model doesn't know how to solve a task, how can it possibly write an accurate, useful rule to fix its own mistake? Wouldn't it just distill its own hallucinations back into its weights?
Yeah, that is the defining pitfall of self-distillation pipelines. But SEED circumvents it through joint optimization.
Joint optimization with what?
The standard RL loss. The on-policy distillation loss, that token-level probability shift, it is not optimized in a vacuum. It is jointly optimized alongside the standard reinforcement learning loss from the environment.
Ah, so the outcome-based reward acts as an anchor.
It acts as the ultimate ground truth. If the analyzer hallucinates a terrible piece of advice and the model tries to distill it, the environmental reward will penalize that trajectory heavily.
Which mitigates the impact of that bad advice on the policy weights.
Exactly. Furthermore, because of that stage 1 fine-tuning we discussed, the model already knows how to extract useful rules, even from failures.
Okay, so when analyzing a completely failed run, it doesn't just output nonsense. It can confidently isolate the local error and output a rule like, do not repeatedly search the same empty drawer.
Yes, it extracts constructive advice from a negative outcome.
Okay, I get it now. The RL loss provides the reality check on the final outcome, while the OPD provides the dense step-by-step breadcrumbs showing the model how to get there.
And the best part is, because all of this probability shifting happens during the training loop, the analyzer role is completely discarded at deployment.
So the knowledge is entirely baked into the policy weights.
Yep, you run the base policy as usual. No retrieval modules, no extra skill banks to maintain, and no augmented prompts eating into your context window.
The theory makes total sense. For the ML practitioners listening, though, the real question is how this translates to actual benchmarks.
Of course the numbers matter.
The researchers evaluated SEED across 3 domains: ALF World for text-based embodied interaction, Web Shop for interactive web navigation, and search-based QA.
Really rigorous benchmarks for agentic behavior.
Yeah, and I mentioned the qualitative candle in the toilet example earlier from ALF World. It's hilarious, but it really highlights the difference between outcome-only RL and token-level distillation.
It really does. The baseline GRPO agent getting stuck in a hallucination loop with the toilet paper is a classic symptom of sparse rewards.
Because it knows it needs to interact with the environment, but it lacks the fine-grained logical sequencing to recover from an unexpected missing item.
Right. The seed agent, by contrast, demonstrates coherent, goal-directed recovery. It notices the candle isn't immediately visible, deduces it needs to check plausible storage locations, systematically checks the shelves, finds the candle, and completes the task.
I know that qualitative difference translates to the macro averages, but I wasn't entirely sure how to contextualize the numbers they reported in the paper. Can you break down the actual performance leap we're seeing on ALF World?
Sure. Depending on the underlying model scale used for the experiments, seed increases the macro average success rate on ALF World by 14.9 up to 45.9 points over the standard GRPO baseline.
Wait, a 45-point jump is massive. That's moving a model into a completely different tier of reliability.
It is a profound capability unlock. But for anyone managing a compute budget, the most compelling data point is actually the sample efficiency.
Oh, because it learns faster.
Yeah, because seed extracts such high-density supervision from every single trajectory, it requires far fewer environment interactions to converge.
What were the actual numbers on that?
In their tests, a seed model using just 60% of the training data actually outperformed a standard GRPO model using 100% of the data.
That is wild.
Yeah, specifically on ALF World, the 60% seed model hit a score of 80.7, while the full data GRPO model peaked at 75.0.
That is a critical detail for ML teams, because environment rollouts are notoriously slow and expensive during RL training.
Extremely expensive, yeah. You're simulating an environment over and over.
If you can cut your rollout requirements by 40% and still achieve a higher success rate, you are saving thousands of GPU hours. That dramatically lowers the barrier to training capable long-horizon agents.
And we know the model isn't simply overfitting to the training environment to achieve those numbers either.
Because they tested generalization.
Exactly. The researchers tested cross-domain generalization on unseen ALF World task splits, and seed maintained a plus 15.3-point advantage over GRPO.
So the token-level distillation forces the model to genuinely internalize reusable behavioral strategies rather than just memorizing the specific rooms it encountered during training.
Yes, it learns the actual underlying skills.
I saw a chart in the paper detailing the training dynamics over time, specifically looking at episode lengths, but I wasn't entirely sure how to read the drop-off they highlighted.
Oh, that graph. Yeah, it's really interesting.
Can you explain what is happening as the training steps progress?
That graph is essentially the mathematical representation of the candle example.
Oh, really? How so?
Well, early in the training run, the seed model hits around a 57% success rate by step 40, while GRPO is still struggling down at 35%.
Right.
But simultaneously, the average episode length for the seed agent plummets rapidly. It goes from averaging 28 turns per episode down to roughly 13 turns.
Wow. So it's trimming the fat off its decision-making tree.
Exactly.
It's not just succeeding more frequently, it's succeeding with high efficiency. It stops the unproductive wandering and takes the direct path to the goal.
which proves that the bottleneck in Agentic RL isn't necessarily the base model's latent capacity to reason. The bottleneck is the quality and density of the feedback it receives during training.
It just needs better guidance earlier in the loop.
Right. When you force the model to reflect on its own experiences and mathematically align its base policy with its own best hindsight, you unlock capabilities that outcome-only RL simply leaves dormant.
So, to summarize for our highly technical audience building the next generation of agents, this deep dive into the paper shows that SEED offers a highly practical blueprint.
It really does. It's very actionable.
It bridges the gap between outcome-based RL and token-level optimization. By acting as its own hindsight analyzer during the training loop, you secure dense on-policy credit assignment.
And the downstream benefits are huge.
Yeah, you drastically improve sample efficiency, which saves compute, you boost zero-shot generalization, and you achieve all of this with zero added latency at deployment. It is an incredibly elegant solution to the sparse reward problem.
It represents a significant step forward in self-improving systems, that's for sure.
Definitely.
But, as a final thought for the practitioners out there to mull over, SEED currently relies on extracting natural language skills to guide its probability shifts.
Right, the analyzer outputs an English sentence explaining the strategy.
Exactly. But as we push toward continuous, lifelong learning agents whose trajectories span days or weeks rather than 30 steps, will natural language remain the most efficient medium for hindsight?
Oh, I see where you're going with this.
Yeah, like, will future iterations of self-evolving frameworks distill hindsight into abstract, continuous vector representations instead?
So you mean the model would be generating alien skills that we as humans can no longer read or debug?
Exactly. It would optimize token-level behavior in complex, high-dimensional ways that human language simply lacks the bandwidth to capture.
That is wild to think about.
We start by teaching the model to critique itself, like a chef reviewing a recipe in English, and it may very well evolve into communicating its hindsight through mathematical concepts we can't even fathom.
A fascinating and honestly slightly terrifying trajectory for self-improving agents. But, well, at the very least, it knows how to find a candle without hallucinating a roll of toilet paper first.
True.
We will take the wins where we can get them. Thank you for joining us for this deep dive. We will see you next time.